I'm very pleased to have you here for our next laser talk devoted to the black hole. We have done already several links to the research in the space. We had about galaxy, we had about sun, we had about different kinds of the influence, how the space and sun coexist. So we had really a lot, and so now this is black holes. I think it's very logical. So we are Leonardo Talk Brussels, and today we have with us panelist. I would like to introduce you. This is Valery VERMEULEN, Stephane DETOURNAY, and Edith DOOVE. She will moderate this event. Edith DOOVE, just a few words about her. She is a curator, writer, and researcher, especially interested in notion of emergent and contingency cross and transdisciplinary collaboration. She holds a PhD as a member of Trans-Technology Research at Plymouth University, where she is a postdoctoral advisor. Since 2018, she lives and works in France, currently in Rouen, where she teaches at École Supérieure d'Art and Design Le Havre Rouen. She was the curator visual arts for the Arts Festival Vatou in 2023 and currently prepares an exhibition and publication on the research group and their influence on art education for the State Museums and PXL School of Art and Hustles, autumn 2024. And I would like to give a floor to Edith to open our laser talk.
Okay, thank you for coming. Sorry, but I have a cold, so I might sound a bit like I'm in a black hole somewhere. So the recent exhibition Into the Black Hole at the Valkhof Museum in Nijmegen, Netherlands, stated that black holes form the intersection where science ends and imagination begins. For the museum, that was the main reason to bring art and science together in this exhibition. Among the artists involved were Evelina Domnic and Dimitri Galfand, who were our guests for the laser talk we gave at the KIK Festival in Namur last year. Now, Kip Thorne's book, and you had it with you. Famous book, Black Holes and Time Warps, begins with a kind of science fiction story to explore what a black hole exactly is. While he wrote the book in 1994, he mentions, amongst others, a Dame Abigail Lyman, who solved the issue of cosmic censorship in 2023, so last year, and Schechter's Black Hole Atlas, that equally seems to be fantasy. For those who don't know him, Kip S. Thorne is a very well-respected theoretical physicist who was an advisor for Christopher Nolan's cult science fiction movie Interstellar in 2014. Black holes were discovered in 1972, but I learned this evening that the first one was actually more or less discovered in the 18th century already.
The idea. Yeah.
The idea,
yeah.
well. And the idea of a black hole is almost as important as the actual black hole, as I understand. I've been reading Kip Thorne and other books the past couple of weeks, but that doesn't mean that I can pose intelligent questions because I'm not a physicist. But anyway, until the first image of a black hole was made in 2019, and that is the photo that we've used for the announcement, which is actually not a photo of a black hole, it's a construction. And there was indeed a whole lot of imagination necessary, as in principle, a black hole cannot be observed, not even using the best telescopes, because it swallows everything in its surroundings, planets, stars, and even light. This comes from the website of the exhibition Into the Black Hole. Or like Thorne states, black holes down which anything can fall, but from which nothing can return. Imagination or interpretation play thus effectively an important role in the research around black holes and the universe. It's a bit like Alice in Wonderland in a way.
The rabbit hole.
In a way. As Alexandra said, we have two guests. Dr. Valery VERMEULEN is a Belgian electronic musician, mathematician, music producer, visiting professor at KASK and Conservatorium School of Arts, Ghent, guest lecturer at Master Art Science Interfaculty KABK The Hague, and researcher at Antwerp University. He holds a PhD in mathematics and a master music composition. In his practice, Vermeulen focuses on the intersection between music, math, and physics. Topics in his work cover a broad range of disciplines, including algorithmic music composition, generative sound synthesis, AI, biofeedback, psychophysiology, astrophysics, theoretical physics, econometrics, data sonification, and data visualization. If you lost, me too. But he's going to explain it all later. Vermeulen's work has been featured extensively in global news outlets and magazines such as Music Radar, Tech Radar, BBC Six, The Wire, Electronic Sound Magazine, Neural, 15 Questions, New Scientist, DJ Mag, Mix Mag, and etc.
That's a lot.
Yeah, if you don't mind. In 2021, he released the Black Hole album, and that's the most important, I think, for tonight. The Micrometers ADS, I don't know how you pronounce this actually.
ADS.
CFT 001.
Yeah.
Okay. On the label Ash International, a subsidiary of the renowned Touch label. The album was picked up internationally and was awarded in 2022 with an honorary mention for the Starts Prize Arts Electronica, issued on behalf of the European Commission. And Dr. Stephane DETOURNAY is a FNRS Research Associate and Professor at the Université Libre de Bruxelles and the International Solvay Institute. He was the holder of a Marie Curie Fellowship, is an honorary BAEF alumni, and received the 2016 Adolphe Wetrams and 2020 the Donder Prizes from the Belgian Royal Academy of Science. He said this, so I read. He held postdoctoral positions at the University of Milan, UC Santa Barbara, and Harvard University. His research interests lie in the area of high energy and gravitational physics, with particular focus on quantum aspects of black holes. He's also interested in outreach and in establishing connections between arts and sciences, being in mixing sciences, music, and smoky cocktails, throwing sellers into a black hole to check how it sounds, or discussing the nature of reality with illusionists. So, interestingly enough, so tonight we have two guests who are a mix of both scientists and art. Both of you are, or at least you have a large interest for it. So, before I'm going to ask any kind of stupid questions, I invite you, Stephane, to present and just go. If you think it's too long, I will say.
You can cut me because
yeah. Okay.
Just tell me when I should stop.
Yeah. Okay.
Well, thank you very much for the very kind introduction, and hello everyone. Very happy to be here, and hello to my family watching. I hope they are. Okay, so indeed, my name is Stephane DETOURNAY, and I'm working at ULB. So I'm an FNRS research associate, and so I work at ULB where I do research but also teach, and I'm also trying to do outreach because I find it fun, like tonight. So I'm very happy to be here. Okay, so what is the sort? So here, I will just start by talking a little bit about my research and how this fits. I mean, how this will maybe fit with Valery's activities, and then we can maybe digress and come back to research and whatever. So don't hesitate to interrupt if you have any questions. So the general scope of my research can be put in maybe one word, and it's something that is called quantum gravity. So it's a kind of like broad word that encompasses a lot of different fields. So quantum gravity has inside something that we call string theory or holography, and it will contain one of the main topics that we will be dealing with is black holes. So is not limited to this, but these are the aspects of quantum gravity I'm working on and that I know better. So those are the ones I want to talk about. I'm not going to really talk about it in deep detail, but if you have any questions, we can discuss it later. So what is quantum gravity? So the answer is actually that we don't know. So that's it. Good night. Well, actually, we don't know yet. So that's an active field of research that involves like lots of researchers around the world. But so let me explain how we define quantum gravity, which is something that we don't know. But at least let me set the stage and explain what we think it is. So you might have heard that the physics of the 20th century is based on two pillars. So there are two major theories that were invented more or less at the beginning of the 20th century, and on which basically all the physics that we know today, I mean, derives from. So one is general relativity. So sorry, that's in French because I just cut and paste from something that I did before, but you will understand later why. So the first one is general relativity. So the famous theory that was, found by Einstein at the beginning of 20th century, 1915, where space-time is curved. You might have heard with weird phenomena. You have we have black holes. We'll come to that later. So that's the first one. And the second one is quantum theory. So usually you might have heard that we talk about quantum mechanics, but more precisely, the thing that we have in mind when we talk about these two pillars is really something that is called quantum field theory, and it's something that really governs all microscopic interactions in the world. You might have heard about the CERN do experiments. They clash, they smash particles at each other to make other particles. We observe the Broad-Angler-Higgs boson. We observed this a couple of years ago. So this is really based on a theory that is extremely, extremely messy, complicated, but very precise, that is called quantum field theory. So we have these two theories. Now, so what are these two theories in a couple of words? I'm not going to do a lecture on these things because it will be maybe too long. But the first one is general relativity. So what is general relativity? That is the modern description of the gravitational interaction. So at school, you might have heard about Newton's laws, that two masses will attract with a force that is inversely proportional to the square of the distance. Maybe you remember. If you don't remember, that's okay. So that's Newton, and that's classical mechanics. But actually, Newton's theory was shown to be not wrong, but actually limited to some only weak masses regime, and that was supplemented and replaced by a theory that is called general relativity that appeared in 1915, and that's one of the greatest contributions of Einstein to sciences, as you might have heard. So general relativity is really the theory that applies when you are in situations where gravity is dominant. So gravity is the main force. But gravity is an extremely weak force. If you take, you take a needle and you just want to make it compete. You take a needle and you take a little magnet, and you're going to drop the needle. So you'll have two forces competing. So the electromagnetic force of the magnet, which is extremely, you can buy this for €2 anywhere, and the gravitational force of the whole Earth, which is 10 to the 24 kilos. So that's huge. So who's going to win? Well, if you hold a magnet, well, the electromagnetic force is going to win. Like a stupid magnet, €1, that's going to beat the whole mass of the Earth. So the gravitational force is extremely, extremely weak. But the thing is the point is that it's never screened. So at large distances, where all the other forces compensate each other, gravity will win. So this is why when you want to describe, the solar system, you want to describe cosmology, evolution of the universe, motions of galaxies, general relativity is the main interaction, is the main theory that we will use, and gravity is the main interaction. So GR, I'll say GR in the following. General relativity is a bit. All right, so that it applies at large scales where gravity is dominant. Okay, so that's what it is, and we are somewhere here. Then the other theory is quantum theory. So as I said, quantum theory, quantum field theory, or the standard model of elementary particles, that's something that physicists use, that governs the behavior of elementary particles. So that governs the microscopic interactions of electrons, protons, neutrons, all the things that make them up, quarks, and all these things. And the quantum theory pertains to the microscopic world. Quantum theory is a really complicated thing, and there are all these funny sentences about extremely brilliant physicists that say that if you think you understand quantum mechanics, that means you don't understand quantum mechanics, for example. So Feynman said these sort of things about quantum mechanics. We're not going to talk about it. It's an extremely weird theory that has extremely weird rules. So probably, there's the thing that you cannot measure the position and the speed of a particle at the same time. Or that means that you can create particles with a crazy energy if the amount of time that this particle exists is small enough. Yeah, that's the Heisenberg uncertainty principle. There's also the thing with a cat that can be dead or alive until you watch it. So all crazy things, but we don't exactly understand why and how these things work. But once you have the theory, you can compute stuff. can make predictions, compute the probability that certain phenomena will happen. You can compute certain coupling constants in certain theories, and you realize that the computations that you make and the experiments that you make, you execute to compare them to the predictions, are extremely in agreement. So these are the experiments that are verified, that have verified a theory with the best precision ever. So even though it's a crazy theory, we don't understand how can a cat be alive and dead. This completely doesn't make fucking sense. But actually, that theory has been verified with an extremely great and great accuracy. So okay, we have these two theories, and that one applies when things are really, really small. So for example, inside your smartphone or whatever, where you have semiconductors and all these things. That is governed by quantum theory. And you are here now. So now the problem is that these two theories actually are incompatible. So one works extremely well when the distances are small and you have all these weird quantum world, and where you can neglect gravity. And the other one works extremely well when the distances are really large, so you don't care at all about the quantum effects and these weird uncertainty principles and stuff. So these two theories, when you try to put them together, that doesn't work. You get just complete nonsense. You try to mix them, take the principles of one and put them in the other, you get completely crazy stuff. Okay. But then why would you care? I mean, I just told you that usually we don't fucking care about this because we just either like it's really small and we need quantum theory, or it's really large. So why would you ever care about combining these two things? Well, first, as a matter of principle, and also what the history of sciences has told us, that as soon as you have two theories that work extremely well in their regimes of validity, and then when you try to combine them and everything breaks loose, that actually means that these two theories were incomplete. So you could say, okay, these two theories are incomplete, and that is fine. But what the history of sciences has told us, that when you try to fix the fact that they are in contradiction, well, that brings you to have to elaborate a new theory. And sometimes it happens that new theory is completely different in spirit and in construction than the original theories. So it can completely shift the paradigm. And I will just give you a couple examples of this. So here, okay, well, we have these two theories that are incompatible. For example, general relativity just was built out of the contradiction of two theories. One is the Newton's law, the laws of Newton that you might remember describing gravity in high school, or maybe in bachelor if you did sciences. Newton's laws that if you have two masses, they attract themselves. Okay, you can compute that force. But then you have also special relativity. Special relativity is this theory of Einstein. That's one of the biggest theory of Einstein that told us that nothing can go faster than the speed of light. And Einstein, when he built that theory didn't have gravity inside. But then he said, okay, I'm going to incorporate gravity into my theory of special relativity. But that theory was telling you that nothing could go faster than the speed of light. The problem is that in Newton's theory, everything goes faster than the speed of light. Well, interactions goes faster than the speed of light because you have a mass and then you have another mass. If you just make that mass disappear, instantaneously, the force will disappear. That means that, for example, you probably know that thing, that the light of the sun takes 8 minutes to reach our eyes. So actually, we see the sun. Well, if we can see the sun, that's a bit hard these days. But okay, we see the sun like it was 8 minutes ago because it takes 8 minutes to the photons of the sun to reach our eye. But it also means that in Newton's theory, if I just destroy the sun, I don't know how to do that, but imagine I destroy the sun, instantaneously, the Earth will start going in a straight line. Okay, because the Earth goes around the sun because of the mass of the sun. But no, if I destroy it, the Earth will go in a straight line. But instantaneously.
Is it theoretically or is it proven?
Well, if you apply,
No.
I'm just curious.
The thing is that in physics, you never prove anything in physics. You cannot prove Newton's laws. There's no physical law that you can prove. All the best you can do is having a law and checking that it works. I cannot prove you that it will work in any situation forever. But no, if I check it, I will say that law has an extremely good probability to be verified. And Newton's laws are extremely well verified in their regime of validity when the masses are not too big. That means that if I apply Newton's law to the sun, indeed, if I make the sun disappear, the Earth will go in a straight line instantaneously. But that doesn't make any sense because special relativity, Einstein told us that nothing can propagate faster than the speed of light. So something instantaneous goes at an infinite speed, and that's obviously faster than the speed of light. So Einstein wanted to reconcile these two theories. Speed of light is a maximum speed, and Newton's law has infinite speed, and that brought him to general relativity. But general relativity is extremely, extremely different in spirit than Newton's laws. It gives the same results in some regime, but it gives better results in other strong field regimes. So that's one example. Then there is a couple of other examples. For example, special relativity itself came out of the contradiction between electromagnetism and Galilean relativity. We can talk about it. Yeah, it's just because I wanted to draw a nice little picture with all these things. So just to tell you that actually most of the major physical theories of the 19th, 20th century, they actually were born out of a contradiction of two existing theories. So you can ask me questions about it if you want. So the base theory of physics told us that contradictions are good, and actually one of my mentors when I was in my postdoc years, I ripped that drawing from him. I just redrew it, but this is in one of his talks, and he was using this motto that contradiction leads to progress. So okay, now what is the contradiction here? I told you that when we try to take quantum mechanics, the quantum theory, and general relativity, try to mix them, we get nonsense. So what exactly is the contradiction here? Actually, there are at least two situations. So I told you that usually we don't care. We don't care at all. Either we have gravity, large distances, we don't care about the quantum theory, or we have small distances and gravity is just too weak to be important. But actually, there are two situations where we really have to combine the two, where we really have to combine a theory that has gravity and that has short distances. And these two situations are the following. So the first one is the Big Bang. So the Big Bang, the Big Bang theory actually it's a TV show, but it's also a theory. Before there was a TV show. So you know that the universe is expanding. So we have observed that if you look around you, all the things around you seem to be like receding from you at a certain speed. So the universe is getting bigger and bigger and bigger with time. This is something that was predicted. That was almost predicted by Einstein, but then he messed up his computation and he said that the universe was static, actually. But the universe, so it's actually Lemaitre and Friedman and all people like that people that predicted the universe was expanding. And then Hubble observed indeed that looking around him, that all the galaxies, if you look there and there and there, all the galaxies seem to go farther and farther away from us. So the universe is expanding in time. But that means that if we rewind the time, there was a time where the universe was getting smaller and smaller and smaller and smaller and smaller. So that means that at some point in time, and actually in space, the universe must have started from a really tiny, tiny region. And so that means that the whole content of mass and energy and whatever you can imagine on Earth, in the universe, that everything was contained in a really tiny region of space, time. So that means that there was actually a really strong mass contained in a really small region. So distances were small, masses were big. You need both to describe gravity, and you need at the same time quantum theory. So this is one situation that actually our current theories are completely unable to describe. General relativity, quantum theory cannot say anything about the Big Bang. If you ask me, I don't know. And if you want to know how the universe started, we don't know yet. So that's the first situation. So the second situation is the one we'll talk a little bit more about. It's black holes. Okay, we'll talk more about black holes. I don't want to say too much about it, but actually, so black holes essentially are regions of space-time from which nothing can escape. So we'll make that thing a little bit more precise, but essentially it's so massive that not even light can escape. That means that it's actually a region. So if you see this drawing there, so if you're like hanging out here and cruising, yeah, that's fine. You're happy. You can live a happy life. But now if you get closer and closer, you see that the curvature becomes a little bit more dramatic. And then there is this region here that's called the event horizon. That means that if you cross this region, you will never ever be able to get out of that region. That your future, once you cross that horizon, will be to end and die here at the singularity.
But this may also because sometimes it's confusing. This is when we suppose that we would live in a two-dimensional world.
Yeah.
Voila. So as physicists, because otherwise,
Can you speak?
yes. It's you assume that we live here in this drawing
In a 2D
in a
world.
two-dimensional world, that we don't have 3 dimensions, because otherwise it's very difficult to imagine.
And it's really hard to draw because
You cannot draw
we
it.
didn't get the budget to draw like a 3D 3D sheets of paper. And but you can view this a little bit like, there's an analogy that people makes, like imagine you have a waterfall, and the waterfall is where you die because it's like really steep and really dramatic. And if you're in a little boat, and if you don't go too close to where the stream becomes really strong, you can go in there and look a little bit, and then you go back, and that's fine. But if you cross this region where the stream is so hard that if you turn around, you try to row as fast as you can, you try to row at the speed of light, even rowing at the speed of light, you are just like brought to the singularity, and you crash at some point. So that's called the event horizon. And there's many things to say about black holes, but black holes really are just, if you have to remember one thing, are regions of space-time from which nothing can escape. So that's it. There are many questions actually about black holes that are unsolved, because of course the thing is that this region here, this is the region where all the mass of the black hole is concentrated. So again, we have a really tiny region in space-time where a huge amount of mass is concentrated. So again, you need a theory that has gravity, and you need a theory that has quantum effects to describe these particular regions.
Is this then the Big Bang in the opposite side?
There are a lot of analogies.
Yeah.
There are a lot of analogies. It's not exactly the time reversal. It's not exactly this, but there is a lot of analogies between the two things. Yes.
Because you have here a horizon now in the black hole, but you also have a cosmological horizon.
You also have a cosmological horizon. There is a fact that we cannot see the whole, so we don't have access to the whole universe. So that thing means that once you're inside here, you have no access. You have access. You cannot communicate what's outside the horizon. You can get information in. If your family is there, then you can shout at you and say, come back, and you shout back, but actually they will never hear you. So there is a region that's disconnected from the rest. And in the universe, you have something like this. And that's also related to the fact that the speed of light is finite. So you cannot communicate to anywhere for which the distance is bigger than the speed of light times the time of the universe, because you won't have had time to travel there or to send a signal back there.
Yeah, and also the universe is accelerating.
Yes.
So it's accelerating, going faster and faster and faster and faster. But if there's a point too far, then you can calculate a light wave that you would have to reach you. If it reaches you, the universe already doesn't exist anymore. So it's too, or... And that's also...
Would I say that?
Yeah.
You will leave this room completely confused. Just so
Yes.
Yeah, maybe.
Yes. No, indeed. Yeah, indeed.
Maybe it's not the moment to bring it up, but there's also different scales of black holes.
Yeah, sure. Yeah. So indeed, I didn't mention this, but you can have black holes of any size, actually.
Yeah.
We always imagine that the black hole is something that is extremely big and extremely massive, but actually, to build a black hole, you only need to concentrate a certain amount of mass in a certain radius, and that's it. So you can really have a black hole the size of a virus. You can have a black hole the size of a virus will be like many tons, but you can have a black hole the size of the mass of the Earth.
Mm-hmm.
That will be like a little cube, like a thimble, or a centimeter cube.
Because it's so heavy.
They make little black holes.
No, they're looking for.
People were thinking that in accelerators you would be able to make them, and actually they haven't, as far as I know. But actually, there's nothing to be scared about, actually, because also there is this thing that black holes evaporate. So small black holes evaporate really fast. So that's even if they were formed, they would evaporate like extremely fast. There was also arguments that if black holes could be formed in accelerators like this, that would have been done like a lot of times before, because the phenomena that happens in accelerators, they happen like every day, like millions of times in the atmosphere, for example, with gamma rays and these things. So since that never happened there's little chance we will be able to make them in accelerators.
It would be nice if we found it.
Well, there might be, alien civilizations using black holes to store information. I mean, I don't want to lose everybody. But black holes, what do you want to say? Oh yeah, so I think maybe at some point we might return to how black holes exist, what kind of black holes exist. Maybe I'll say a word about this later. I think.
Yeah, that's fine.
But at least from a theoretical point of view, black holes exist. We'll talk about it. We can see them. Even though they are black, we can see them. But there's a lot of things we don't understand about them, because to understand them, we would need a theory that has at the same time gravity and quantum effects. And the three major things that we don't understand about black holes are the following. So the first thing is what happens at the singularity. So indeed, I just told you, there is this little region where all the mass is concentrated, but there, all the theories we have are completely unable to describe the physics. So we don't know what happens at the singularity of a black hole, because it's really strong mass and really small distances. We don't have a theory that explains this. And then there are two other problems that are not exactly related to the fact there is a singularity. They are more related to the fact there is a horizon. There is this like no one-way surface. And related to the existence of this one-way surface, a surface that like splits the universe in two, if you will. There is one region, either you're inside or you're outside. And if you're inside, there is no way you will communicate with the exterior. And related to the existence of the horizons, there is this question about like the fact that black holes destroy information. If you take your favorite book, or you take
Your favorite cat.
anything, you take a Schrödinger cat or whatever, okay, you throw it inside the black hole, you will never ever be able to know what happened to that book. It's really different. You can tell me, well, but I can take a book and I can burn it, and then I destroy the information in that book. But that is slightly different, because when I take a book and I burn it, I will remain with the ashes. I will remain with maybe some pages won't have burned, and also there is the smoke. There is the photons that will have been emitted by the book burning. So actually, in practice, the information has been lost. But in theory, the information is still there. Everything is available.
It depends if you have read it or not.
If I've read it, of course.
Yeah, because that's an electromechanical process. It's a biological process in your brain. Yeah, but if you're thinking about information theory, it's about recycling. We all know that we are made out of stardust, because everything that we are made of comes out of the cores of stars that's being recycled. It's not because we are alive. Well, what's the definition of being alive? That we have for the nature. If you're burned, it has the same value, or it's the same. It's just transformed.
Yeah, just carbon and hydrogen
recycling.
And stuff.
Yeah.
Well, it's not quite. I mean, I wouldn't say this because defining life.
Yeah.
It's another question, but it's an extremely difficult
Well, we
problem.
won't go there.
No.
We won't go there for now.
I need to speed you up a little bit.
No, okay,
then.
sorry. I will.
Yeah.
Okay, so do black holes store information? So we talked about the book. When you throw something inside a black hole, that will never be recovered. Okay, we can discuss about radiation about a black hole, but it's really different because of that like one-way region. So when you throw something into a black hole, essentially you would think that's the best way to hide your secrets. If you have a diary, you throw it in the black hole.
It just projects it on the outside.
I don't know. In principle, it's on the outside. What outside? There's no. Sorry.
It's a hologram.
Okay, you're spoiling me a little bit.
Yes.
The thing, it might be that the information is stored at the boundary of the black hole or at infinity with radiation. This we actually don't quite know about this. But okay, so if I can say your word. So we believe that they don't destroy information. We can talk about it later. But that's still an open question. There is no consensus about this. And then there is another question that's more the question I'm interested in, but I will just say like a little word about it. How can black holes are extremely paradoxical. So they are at the same time, they are the coldest and the warmest object. I can tell you why later. They are the quietest and the more violent, but they are also the simplest and the more complex. So the simplest, how to explain this? So the black holes are extremely simple because they are a little bit like elementary particles. If you have two black holes that have the same mass and the same spin, they are exactly the same according to general relativity. It's the spin and the mass is like an elementary particle, like an electron, a proton. They have a mass and they have a spin. So according to general relativity, black holes, they are only characterized by a really small number of parameters, essentially mass and spin. But on the other hand, if you take general relativity from another point of view, you are led to the fact that black holes have an entropy. So, okay, what is entropy? Entropy is essentially a measure of complexity. So, yeah, I think I'm going a little bit but essentially, black holes are also, so while general relativity is telling us that black holes are extremely simple, just mass and spin, the black hole, that's my name. But also, physicists like Bekenstein, Hawking, and many others have shown that black holes are extremely complex. Actually, they are the more complex objects in the universe. By complex, I mean that you can store information in them in a really, really effective way. So that means I think there is a number, you can store the whole Google database in the black hole that is 10 to the minus 24 millimeter. So 0 times 0, 0, 0, 0, 24 zeros and 1. That fits all the Google database. So it's extremely, extremely useful to store information. No, the problem is extremely hard to extract the information out of it, of course. So I wouldn't advise.
Because it's not necessarily organized.
So that's exactly this. Yeah. So black holes store information in an extremely scrambled way, in the most scrambled possible way, actually. Mm-hmm. So there are. And then recovering it will take you a huge amount of time to be able to reconstruct that information. Yeah. That is true. Yeah. But at the same time, how do we explain this complexity? When you have a glass of water, we know to explain the complexity of the glass of water, we just count the molecule. We don't do this, but we just count the molecules that form the glass of water. That explains the entropy of the glass of water. But for a black hole, they're extremely complex, and we have no clue of what the molecules of the black hole are. Mm. So that's a big question. Okay. Then we can talk about string theory later, but that we have no clue about.
I think you will maybe also talk about string theory.
Brain theory, brain cosmology.
Yeah, you also, because you mentioned it. So there is one word I understand in Valery's presentation. There was lots of things. There was ADS CFT, which is one actually. It's a topic actually we work on that's related to string theory. Maybe we'll
maybe can you sort of try to speed up?
I will. I think I'm sort of.
I find it really interesting, and I hope you too. But at some point.
So maybe I will just conclude with that thing, and I will leave because I was also explaining my interest in the connection between sciences and arts. But then maybe we can let Valery talk, and I will
some connections.
But then I will just finish with one question, a burning question that probably everybody's asking. So can we observe black holes, and do they exist? Because I thought there's black holes. This is terrible. Do they exist? Are there black holes? Actually, there is a huge number of black holes. Well, we can roughly estimate how many black holes there are in the universe, and probably they are 1 with 19 zeros black holes in the universe. So that's a huge number, because we believe that at the center of every galaxy you have a supermassive black hole that is like millions or billions of solar masses times the mass of the sun. And we believe that a certain fraction of all the stars in the universe, if they're massive enough, will become a black hole. It's like 1% of 0.1%, and there are 100 billion stars and 100 billion galaxies more or less in the universe. So that's a lot of black holes. So from general arguments, we think there are a lot of black holes. Okay, but that's nice. But do we see them? We see black holes. Actually, yes, we see black holes. And you probably saw a black hole, and you probably all saw that picture. So that picture was taken in 2019, and that's the first direct picture of a black hole. So that black hole is completely crazy. I think that black hole is 50 million light years away from us. So, 50 million light years. It takes 15 million years for the light to reach that place. But that black hole is huge. So that black hole, the size of that black hole is 3 times the size of the solar system, or between 3 and 300 or something. So it is huge. So that black hole is it's huge, 3 times the size of the solar system, but it's extremely far. So to observe that black hole was actually as hard as observing, as seeing an orange at the surface of the moon. So this is what these people did. So they built virtually built that telescope that was the size of the Earth. By combining all the telescopes on the Earth, they were able to see that object. And so that's the first picture of a black hole that was taken 5 years ago. And actually, okay, there is a small video of what we are actually seeing. Because I told you, well, black holes, we don't see anything. Well, absorb light, so nothing is emitted from the black hole. What we're actually seeing, so a black hole is actually betrayed by its environment. So a black hole is betrayed by the light that is emitted around it, that didn't fall in the horizon, and that is deflected by the black hole. So if you look at it, you have light coming from all the universe, from light around the black hole, but from afar, that is deflected by the black hole and that reaches our eye. And this is what we are seeing here. So the image of the black hole we are seeing is not the black hole itself. The black hole is black and absorbs light. But everything that is around emits light and is actually collimated by the strong gravitational fields of the black hole. And we are seeing the light that is orbiting the black hole that way.
Do you also want to show the video of NASA now or later?
I was thinking about doing this later, maybe.
Okay, yeah, that's fine.
If that works.
Then we'll now first have
Yeah.
and then we come back.
Yeah.
Because
You need-
visualization of something that you think of, even of the telescope, combination of all the telescopes is not really physically done. It's a thought experiment, no? Or calculation.
The picture, you mean?
Yeah.
No. The picture.
So there's 2 things. So there's So there are,
But
so there are simulations that we can do. So we can use Einstein's theory, and we can compute how light will propagate in a black hole geometry, for example. This we can do, and we can make simulations. But that object that picture that you saw, that's a real picture.
Okay.
But it's not a real picture because the wavelengths is not like visible, but it's a real picture. It's like in the X-ray.
But it's also constructed using artificial intelligence, because what they did was like they filled in the gaps scraping all the images of the internet, and then using some AI algorithms, because that made it so difficult to fill all they had a very blurry idea, and then they filled everything using AI. That's
and you can see the picture is extremely blurry, but actually these things are but it's actually real light coming from 50 million light years away.
Old light. So,
All light, yes. But the real spectrum of the black hole, that's in the X-ray spectrum, so we cannot see them. So they put some color, so they just shifted the spectrum to make it visible.
So the image is 50 million light waves.
Yes, so we are seeing that thing like it was 50 million years ago. Indeed. So that thing maybe does not exist anymore. Could be that the thing has disappeared since then. Yes.
Or has become something else.
Or it has become something else, which actually it's also true for us. I'm seeing you the way you were like a fraction of a microsecond ago.
Yeah.
So it's just,
I hope for the better.
you look good.
Thanks.
I ask another question.
Yes. Yes.
Because you explained the different sizes, and so you said that one is several solar systems. What is the event horizon? And
yes.
What is actually, because what is inside there we don't know, and
yes.
sometimes they say it's like an infinitely small volume, which would mean that for all of them, all the mass that is in there is in an infinitely small volume.
The thing is that sorry.
Yeah. So the size is just the event horizon, but what is in there we don't know, I guess.
But it's essentially empty. So inside the event horizon, it's actually matter that has fallen inside, that's whirling towards a singularity, and that's actually crushed, because once it reaches a singularity, the tidal force is extremely big, and so everything is supposed to be crushed, but we don't quite know. Okay. The thing is that the bigger the black hole is, the longer it will take you to reach the singularity. But for example, for an astrophysical black hole, it will take you like a fraction of a second to reach the singularity. So the time you live inside the horizon is kind of short, unless the black hole is extremely, extremely large. So that this is why we have this picture in mind, that once you cross the event horizon, it's essentially void. You won't hit anything inside. It's essentially empty, and all the mass is concentrated at the singularity, but we don't quite know because we don't have equations or a theory
But
describing
there's also the problem that inside, if you look at the equations, inside event horizon, time and space switch position. So that's also thing that you could go right to your future, and then you can be in your past. I mean, that's another. It's a hypothetical construction, but some theories.
I think So what Valery is saying is that indeed, so there is this. So I told you, once you are inside the horizon, you have no choice but finishing at the center of the black hole and like being crushed.
Yeah, right.
And this is because usually we have two different coordinates. We have a space coordinate, so I can move like this, I can go forward, and I can go backward. That's fine. I can move in both directions. But my time is always moving forward. I cannot look like I used to look 5 seconds ago. Inside the black hole, things are inverted. So inside the black hole, the coordinate that becomes the one that you have no control on is space. So you have no choice. You start. So this is the center of the black hole. This is the horizon. Here you're fine. And then once you enter the horizon, your space coordinate always has to go forward. Well, actually decreasing, ending at r equals 0, which is a singularity. So there is this special character that you cannot do anything but ending at the singularity if you're inside the black hole.
But you could
time can go to
the
left, to the right.
Yes, you could control your time because
in a way, but time doesn't have the same meaning inside. It's not like it doesn't measure your aging, for example,
Okay.
But indeed there is this weird stuff indeed that time and space seem to be switched.
Yeah. Okay. Valery.
Yes. So I will talk a little bit about how I came about working with black holes and music. So originally, maybe you recognize a little bit of this stuff.
There's a title there. I'm joking.
Yeah. So this is my PhD from a long time ago. So once upon a time, I studied mathematics, and it's really nice that you say quantum gravity, because the reason of studying mathematics was because I was, as a teenager, really, I wanted to do two things, make music and work. Maybe my dream was to work on quantum gravity in one way or the other. That was a little bit the two aims that I had. And that's why I started studying mathematics at Ghent University, and I did a PhD it's in the mathematical part of superstring theory. So it's really mathematical at that time. And after my PhD, I had the idea to go towards more theoretical physics. But at the same time, I was always interested in music, also playing instruments and making music from when I was, I think, 5 years old or something like that. So after that, I switched more to music. I started combining my musical interest with mathematics. So I worked at the musicology department, IPAM. It's an institute in Ghent. It's a little bit one of the first electronic music studios in Belgium, long time ago, and now it's a research center. So I did research there on music, artificial intelligence, and emotions. And out of that grew a project. That was the first project that I did. So that was before I was combining theoretical physics and music, but I do more today. So one of the first projects that I did in that direction was called EmoSynth, and the idea was to build, so it's a long time ago, now AI is exploding again, so it's a long time before the AI explosion. The idea is we wanted to build a system that can automatically generate music, and the music would adapt itself to your emotional reactions, so it would know which kind of music it had to generate to get you in which kind of emotional state. You see here this testing person, she has biosensors. Using biosensors, so he's using heart rate measuring devices and stress level measuring devices. We had a whole system programmed using, for people who are into AI, genetic algorithms. So it was in 2007, so at that time, you had to program everything in C++ for people who know coding. So today, with the whole expansion of AI, it really exploded. So we did some performances. This was in Brussels at the Music Instruments Museum. So a long time ago. This was in Ghent.
So you were adjusting what you were playing to the emotions of the person?
The system, well, you had to train it. You had to train it for the person who was listening to it. So we took a testing person, and the system was trained for the test person to get them in 4 different kinds of emotional states. So because you can only track the intensity of an emotion using biosensors. So low intensity, low medium, high medium, and high intensity. And then it's like AI, you train, the system generates music, sees how the person reacts, and it gets smarter and smarter and smarter. And once you've trained it, we use it to make soundtracks automatically for Mute, the Phantom of the Opera. We were using the Phantom of the Opera because we thought it was really nice combining new technology with these old ideas. So, it was if we would do it again now. I mean, I see a lot of more possibilities. But you only have one life, so yes. After that, I switched because, of course, I started studying after EMOSynth composition at KASK, Conservatory School of Arts. So that's an art school in Ghent. So I come from Ghent. And I studied there music composition. So we have it's a program on music production. So it's basically composition for pop music. So, and after that, I found ways because I was a little bit with EMOSynth. We did a lot of performances, but I wanted to explore new territories. So, and again, the question of quantum gravity, it never left my mind. I was like, okay, how can I? And then there was a good occasion. It was the Dutch Electronic Arts Festival. It's a biennale in Rotterdam. It doesn't exist anymore. But they asked me to make a piece on space and music. But it was, for me, I never did anything like that. So I was in my studio. I was trained to make pop music, so far away from... and then I started using my imagination. Yeah. So I was thinking like, okay, because I worked a little bit in the very commercial sector of the electronic music scene, and I was really fed up with it. I was like, it's not my piece of cake. So I wanted to have new ideas. And then I stumbled upon the field of data sonification. So at that time, I didn't know it yet. I don't know if people are aware of, because it's growing more and more popular. You see it more and more. So basically, sonification is a scientific domain in which scientists are using sound to get insight into data, to represent data. Normally, you use a screen, you look at the data, you make plots and stuff like that, but you can also turn them into sounds, and then you can try to figure out new relations in the data, structure in the data using your ears. So, of course, it's a very cool domain to also use as a musician. Yeah. So, of course, yeah.
I think at some point there is one thing that we try to do, like to represent some phenomena that happen
with sound.
Because so you might have heard also that if you are around the black hole, time flows in a different way. So gravity affects time. For who has seen Interstellar, the movie Interstellar here? Okay, so if you remember, there is one thing that happens in Interstellar is that when they are coasting and surrounding that planet, but they cannot stay too long around that planet because one hour close to that planet is 7 years on the Earth. And of course, he wants to see his daughter again. So if he spends too much time around that planet, I mean, his daughter will be too old or maybe dead. And that's an effect that actually that's a true effect. Of course, in Interstellar, they used it in a way that was really dramatic. But if you put a clock here or at the top of the building, you will see that the two clocks after one day won't show the same time. So of course, for such a height, it's going to be like 200 of a trillionth of a second. But it's something that you can measure. So time flows differently in different gravitational fields. So there is an effect of this, that if you listen to somebody talking to you and close to a black hole, his sound will be distorted because the frequency will be changed. And so this is something that
is what you show in another video. I think.
Yeah, that's in a video. We can talk about it later. But that is, and it's a way, it's a sonification of the redshift effect. So the redshift effect is like you have like an ambulance coming towards you. The sound changes. So that's, and you have some effect also due to gravity. So you have a similar. That's a kinematic Doppler redshift, but you also have a gravitational redshift. It's a really important effect, and you can represent it with. So this is something we try.
That's an example of. But of course, there's a lot of other ways you can do sonification. There's a very good book. It's a sonification handbook by Herman. It's from 2011, and you can find a free PDF. And there is a whole, it's a whole field. I mean, it's really amazing. It opened my eyes like whoa. But that got me for the Dutch Electronic Arts Festival, making a composition, and I had to have a topic. I like to use my imagination, and I like to tell stories. Also, so I make now experimental electronic music, but for me, I just like to tell for myself stories with tracks. So every track that I make has a different story. I try to, of course, it's a personal interpretation, but that's also the fun too. I mean, you firstly make music because you like it and you have fun, and then you see what happens. So I work with different series. The project that originated from that is called Micromeras. And the idea is to make music using data coming from space, from deep space, and also from models from theoretical physics. I work with several thematic series because I like to tell stories in the music. And the first series, the title is OGLE 2005 BLG 390 LB. So with the other album, the ADS-CFT album, so I had to do interviews sometimes or for radio, and then they were always joking about the title, like what is going to be the hit? And then they were like, but I like to use scientific titles. So this is the name. I don't know if anyone, this is the name of an exoplanet that is situated, Katrina, near the center of the Milky Way. Yeah. Do you know? Yeah, probably, Katrina, you know.
I don't know it very closely yet. I just know this kind of codes, and Focal is it's a survey doing gravitational lensing observations. So it's an optical gravitational lensing experiment, and then they have a date.
To see that they are there, probably.
So what they do is they measure the whole sky, they take pictures of the whole sky, and they detect small variations, and that's how they see, for example, also an exoplanet, but they find a lot of other gravitational lenses, all these kind of transient events, things that change over time, that suddenly change in the sky.
Okay, voila. So then they have this indeed, as Katrien, these funny names.
So it's the name of the star, and then the B is a designation of the planet.
That I understood when I saw, when I was reading about it. Indeed, the B is like to say that it orbits around a star.
What kind of planet is it? Is it like warm, gaseous? Well, not gaseous. But
it's an exo. I don't know if it's habitable. Yeah. This is an artist's representation.
This was found in 2005, and BLG could be a blue luminous giant, and then there's a number, and then.
Okay, so. But of course we don't know. Probably that it's you have to do more research. But for me, it was just nice to. The idea of the whole album was making a sonic representation, trying to get the audience in a sort of a hypothetical journey from Earth to this exoplanet, only with using sound, no visuals. That was a little bit the challenge that I put myself. So first, of course, is how do you get there? So if you type into Google Maps, you will not find how to get there. So you have to do a lot of research how to, which way to go, It's really funny if you start. Of course, first you have to go towards our solar system. So I use a lot of data from NASA and ESA, of course. They have a lot of data and also a lot of sonifications data on the different planets. And I was using own data also that I found from the Voyager satellites, and then I designed a custom-built sonification techniques to turn number streams into data. So for people who are into sound synthesis, software that I was using was Max MSP. That's used a lot. But I also, that was for the next one, I also started using other kind of scientific software. So besides my work as an art scientist, I also work over 20 years as a data scientist. So that's also now coming in very handy. So more recently, as more into AI, of course. This album was, I played, so that was 2014. It was normally meant to be a one-time show, but as things happened, I played more and more and more. It was really fun to do. And out of that grew the idea, of course, and because I still had my interest of quantum gravity, because it was really cool to do this first show and this first concerts with this first album. Also, this album was never officially released because of the data from NASA and ESA. You have to build. Yeah, it's very complicated. Also for the copyrights. Yes. I didn't want to. Yeah.
Even transformed.
Yes. Because I work with a lawyer, and it's still today not clear if you're using sonification and you're transforming it. It's a gray zone. Yeah. So
would they have noticed?
Or they call it appropriation.
Yeah. No, but I mean, of course, I mean, they're on SoundCloud, the tracks, and yeah, just. And of course, because I was really more, I found a way to combine, of course, my interest into physics, that was more astrophysics and music. I wanted to go even more deeper into the theory. And then the next question was, can I really, in some sort of way, combine my interest in quantum gravity and music? That would be fantastic, because then I have the two in one. And then to start that, I was in 2016, I think. I was playing somewhere in Berlin with a group of people that I knew there, and we were talking about, maybe black holes, or because I looked a little bit in the literature of theoretical physics, and then I saw, because it was still since 2001, I finished my PhD in 2001. I was out of mathematics and physics from that time, and then I read about black holes. And then I went to a conference in Frankfurt on black hole astrophysics, just to challenge myself. First, am I going to understand anything that they're going to talk about? Because otherwise I have a problem if I want to do that. And second, are there possibilities, or am I just dreaming, and is it just impossible to? And it was a really very good experience, because there were a lot of interesting, like Juan Maldacena was there, and I mean, a lot of people, of the core people working in the field, were there, and I could understand. Of course, I had to study a little bit before, and I saw ways to do stuff. So that was really the starting point.
Did you tell him about it? So
not yet.
Maybe you need to explain what the ADS-CFT is to people.
Yes. So basically, ADS-CFT is a one easy way to tell it is we are living in a three-dimensional world with time, you could say. And in the world of GR, general relativity, we live in a four-dimensional space-time. But imagine that we were living in a three-dimensional world, just maybe forget about time, just conceptually. Then you could say that everything that happens in our three-dimensional world, you could completely describe with one dimension less. You can throw one dimension away, and you can describe everything in a sort of a two-dimensional reality that is projected. If you look in the clouds far, far away, that lives there, and we are just some sort of three-dimensional holographic projections, we call them. So it's as if you're living you're thinking you're living in 3D, but in fact you're living on a screen. That's basically the holographic.
That's basically what art does. Translate the 3D to 2D.
Yeah.
So
well, in some
I mean,
sort
that's
of
maybe
way.
as a image,
Yes.
the easiest to say that we're living in a 3D world and we make 2D pictures.
Yes, it's very similar. Yeah. And that's well, it's to explain it intuitively, because if you have to explain it mathematically, it's another story. Yeah.
No, but it is true. It's this funny thing that actually, as you say, our retina is actually two-dimensional.
Mm-hmm.
So the way we view the world, actually, if you look at the image of the people in front of you, that's a complete two-dimensional thing. Mm. But of course, your brain is really, really well trained that because of the lighting, because of the colors, because of everything, you can reconstruct that this person is in front and that person is in the back because of the lighting. But it's true that if you had to draw the thing, if you had to draw what your eyes see now, you would just draw something two-dimensional. Mm-hmm. It's a bit, and this ADS...
sorry, I think it's the other way around. You draw something that's three-dimensional into two dimensions.
Well, no, so but your eye views something that is two-dimensional. You don't see in three dimensions.
Two images putting together, it's got three dimensions.
We know it's three, but we see two.
We know it's three.
Yeah,
But it's because you know it. If you had never lived in a 3D world, what you see now is purely two-dimensional.
But that's basically what cubism does. Huh? Sort of knowing that there is a back of a head
Yes.
or another side of any kind of object or human being, and drawing that.
Well, yeah, cubism is all about this perspective.
Yeah,
They-
it's a translation.
It's a different perspective than the.
But I think it's just due to the fact that your eye, where the image is projected, is two-dimensional by construction.
Yeah,
So you cannot represent something.
The physics of your
And
eyes.
it's a bit, well, yeah.
Yeah.
The thing is that maybe to complement what Valery was saying is, so ADS-CFT is also called the holographic principle. And that's a little bit what we were discussing now, how a hologram really is something that is two-dimensional, but that is built in a way that you feel you see through dimensions. The way actually our eyes see a little bit holographic. I don't know, maybe I'm just bullshitting.
Okay, I know exactly.
Yeah.
But,
And that is a way, there is a way to solve problems in quantum gravity. You can try to do that using this principle. But it's rather technical to.
But the other analogy is imagining our universe is very, very, very complicated. You know, it's expanding and everything. But no, imagine a simpler universe, just a cylinder. Just imagine just a simple cylinder here. No, imagine our universe is just the interior of the cylinder. So we live in 3 dimensions, so 2 + 1 dimensions. We can go like this, and time flows like this. So if our universe is a cylinder, so it's finite, well, the holographic principle tells you that you can know everything about what's inside just by knowing what's at the boundary of the cylinder. So that's, and the cylinder, well, a universe that is a cylinder, that's called an ADS space. That's the ADS of the ADS-CFT. That's a universe that's just inside the cylinder. And the CFT is a thing that lives at the boundary of the cylinder, just a 2D thing. So a 3D universe can be described by just a theory that lives at the boundary.
And if you have a problem, to make it a problem with quantum, you need quantum physics and gravity, GR, inside of this cylinder that you cannot solve because the equations are blowing up.
Because we saw that quantum gravity, we don't know how to.
What you can do is you can take the projection onto this boundary, look it in 2D, and the cool thing is, then you lose the gravity goes away, and you're only left with a problem in quantum physics, and that we can solve. And we solve it, and then we go back to this internal, and we have solved the problem.
Sounds easy, but it isn't. So
No.
I think you should.
I will not.
I invite you to continue because the way you say it is like, oh yeah, but
No.
Yeah.
We're not going to. Okay. So, but that's the title of the project was ADS-CFT 001 on black holes. And I was using for that project, I think it started, so I had collaborators to do the project. Oh, the view is starting. So I did a collaboration with Concertgebouw in Brugge, maybe some of you know, Baltan Laboratories in Eindhoven also helped me. And I think Concertgebouw also, they co-produced a piece. They started by getting me in touch with Thomas Hertog. So he's a colleague of yours. He's worked with Stephen Hawking on quantum cosmology, Thomas, so they wanted us to do a collaboration in which Thomas was giving a talk, and they asked me to make music using something connected to general relativity. So I had a meeting with Thomas, and he said, can you do something with gravitational waves? Because they were recently discovered. And of course, I know there were sonifications of gravitational waves. Probably you heard them.
Maybe you have to explain what gravitational
wave is. Just a gravitational wave is so if you have 2 black holes in space, they meet each other. That's a way how there's several ways probably to generate them. If they're close enough, they will swirl around each other, and they can converge to a bigger black hole. And in this process of merging, it's a super cataclysmic event. You will have gravitational waves that are being emitted, and gravitational waves, we say, are waves in the ripplings of space-time. So what on earth, how can you imagine? Well, if you would walk on the earth and you would enter into a gravitational wave, or it goes through you, you would a little bit oscillate. It's a little bit like you oscillate very, very, very tiny amount. Of course, we don't feel it. And these were hypothesized. So they fell out of the theory of GR in 1916, I think. They were first discovered theoretically. And we had to wait 100 years until they were discovered in 2016. It was the first proven that they were existing. Yeah. Yes. Of course, what I did was I used simulations of gravitational waves. So there's databases of simulations of gravitational waves. And so Thomas said, it would be cool to have a symphony with those gravitational waves, but you can easily sonify them directly, but then they sound very boring. It's like, whoop, the sound like goes like in pitch up, and that's it. So it's like, I mean, I just want to do something cool with it. And then Thomas said, okay, you can also represent them in 3D. So there's also a way to represent them in 3 dimensions, and that's what I did for that project. So I computed. So for that, I used scientific software. This is a visualization that's simply done in MaxMSP of a gravitational wave. So what you see here happening here in the center, there's a merger of 2 black holes coming on, and here the black holes now are merging, and the blob structure becomes very irregular. So, and now they are merged. So those 2 black holes. Of course, it's just a blob structure that's evolving, but that is musically also more interesting because you can take 2-dimensional cross sections of that. So that's what I did next. So with the plane, and then you get these kind of evolution structures that evolve, and those are very interesting to sonify. So here I could do cool stuff with it. So yeah.
I didn't hear anything.
No. Yeah. But yeah. Of course, I also use visualizations. This is an onion-shaped model of a gravitational wave that's being emitted here in the center, you see. So it's spreading out. You can also represent them in 1D. You get those beautiful structures, that evolutions of data. For these compositions, so it's out of that grew a whole album. So I made a whole album. I was also using, this is data coming from, so it's not only black holes that I use, these are data coming from white dwarfs. And white dwarfs are a little bit stars that are not heavy enough to become a black hole, basically. And there's a database of a couple of thousand of light spectra. So this is the light waves, how they are emitted and transmitted onto Earth, how we see them. And then I wrote software. So for that, I was using our studio. It's data science software to make music, which was because I needed a synthesizer with 4,000 oscillators. Yeah, if there's people who are into music, or it's very difficult to make that. Yeah, so and modular synthesizer with 4,000. The maximum is 1,000 or something like that. So. Other data that I was using is here I had help from the University of Leuven. It's from a PhD student. He's now a doctor, Fabio Baccini. And these are simulations on the behavior of particles near the event horizon of a certain type of a black hole. So yeah, you will know, yeah, these are the different parameters. So all the numbers above are the different shape of the black hole. So you can have irregular patterns, irregular, but also very beautifully regular patterns. I was also using, that was a collaboration that I did with the University of Alabama, and they were specialized into simulating what happens when you have black holes in a parallel universe. So this uses string theory, brane cosmology, and this is a model of if you suppose you have a 5-dimensional, of course, now it's becoming very weird, 5-dimensional reality. This is, in those 5-dimensional reality, you have branes. Those are 4-dimensional space-times, we call them. And this is our world. So I try to draw a home. You see there, the Earth and the Sun. That's here where we are in our universe. And here you have a parallel universe. That's another space-time. And here we have strings. Strings come in 2 shapes. So strings are basically tiny little energy vibrations, and they make up all the matter in the universe. That's a little bit the idea of string theory. They can be closed or they can be open. The only way to transmit information in brane cosmology between this brane and this brane is using closed strings, and it happens that gravitational waves are completely made out of closed strings.
Can I interrupt?
Yes.
Because in a way, the string theory or the brain cosmology is an example of how the former theories were completed because they didn't function.
Yes, because in the beginning, a
As
string.
you were saying before, Stephane. more or
Yeah,
less.
brain theory came out of, you had in the beginning 4 different string theories. You had several flavors. And then there was Ed Wheaton, he was a brilliant physicist, and
Yeah, so
yeah,
okay, so that brings us like far, but okay, string theory, the idea of string theory is that the
It's
elementary
quite basic to black holes, no?
Sorry?
String theory is quite basic to black holes.
I wouldn't say I agree with that actually, because
Okay.
so they are, I think string theory is essential if you try to understand certain properties of black holes.
Okay.
But actually black holes were hypothesized, whatever,
yeah.
and even actually observed around the time where string theory was being developed. So string
And
theory,
that's around which time?
so it started in the 60s, but
Yeah.
not for the goal that it was designed
Yes.
to.
Mm.
But the big bang in string theory was in the 80s and 90s.
Yeah, okay.
But by then we had already observed a black hole.
Mm.
You know, Hawking and Kip Thorne had made that bet about, is this thing that we saw a black hole, and they had agreed that it was a black hole already.
Okay.
So, but it is true that the problems that I mentioned, for example, the complexity of the black holes. Do we understand? You know, I told you, if you have a glass of water, we know what is responsible for the complexity of the glass of water is the molecules. But actually, for black holes, we don't know. But actually, we know. We know that the molecules of a glass of water, the molecules of water, are actually these strings that Valery is mentioning here.
Yeah.
So the things that makes up the entropy and the really huge complexity of a black hole are these strings. And now, what are these strings? So string theory is just, but strings, when we say strings, you have to realize that these objects have a size that is completely unimaginable. So if you compare, so I was just checking this on the internet, and so the thing is, the size of a string to an atom is the same as the size of an atom to the size of the whole universe.
Oh, okay.
Yeah.
So these
That gives a
strings
bit of
are
perspective.
extremely,
Yeah.
extremely tiny.
Yeah.
So, but these are believed to be the fundamental object of the theory, the same way that when people did particle physics, you have electrons, you have quarks, these are the elementary particles. But what string theory is telling us is that, well, electrons, quarks are not, well, electrons there, but quarks are not elementary, they are made of little strings vibrating.
Yeah. Is the brain then the
No,
elementary?
And so the point is
Yeah.
that, okay, they are not elementary. Okay, so that it's a complicated question, but so the elementary, depending on the range of parameters you are in the theory, that's a detail, but the elementary particles would be the strings, but then that doesn't mean that there are other objects in string theory. So I tell you, a string is something that has one dimension, right?
Yep.
It is an extended object. The string theory has actually other objects that have other dimensions. It has surfaces, it has like volumes, it has hypervolumes. And these other objects that have to be there for the consistency of the theory, these are the brains that Valery was mentioning.
Yeah, okay.
Yeah, the generalizations of, and you can say that there are parallel realities, basically, these brains.
Yeah, maybe just to make a connection, because I love this movie, but so in Interstellar, for those of you who have seen so Valery said something really interesting. He said that when you have two brains, only gravity can propagate between the two brains. Okay, so gravity is gravitational waves. So in Interstellar, there is this whole book that I have here if you want to read it. It's really interesting about the science of Interstellar. It's really big, and it's really, it's a red herring to read it, but it's really interesting. And so when you read this book, you understand in the movie that actually he assumes, so Kip Thorne, the guy who actually imagined the movie, is assuming that our universe is a brain world. I mean, so it has extra dimensions, like Valery was mentioning. So when he falls into the black hole. Remember, he falls into the black hole, and it becomes completely crazy, all these lights and stuff. And then he sees his daughter in his room. What happens there is that he's in one brain and she's in another brain. But he wants to tell her what to do, because he wants to tell her to tell him to go on a trip, but he's already there. So that it's a bit crazy because of like you can have time loops and higher dimensions, but he's there and she's there. He wants to communicate with her, but what Valery told us is that the only way to communicate is through closed strings, because they can move from one brain to another through gravity. So the way he does this, he communicates with Murph in her room through gravitational waves. So the computer helps him to understand how to communicate. Well, it's really easy to communicate with gravitational waves. I can do it. I'm doing this. I'm emitting gravitational waves. Because what I'm doing here is that I'm changing the distribution of mass in space-time. As soon as you do this, you emit gravitational waves, but it's really, really tiny. So this is what he's doing. And actually, when he moves, he does this weird stuff with, he does his little lines and he communicates with the Morse code and everything. He's doing all this through gravitational waves because that's the only way he can use to communicate from one brain to another.
Okay, back to Valery.
This is a good connection because the people in the University of Alabama, they provided me data of simulations, what happens when you have a gravitational wave coming from the parallel universe by a merger of two virtual black holes and how they enter our reality. So that was also data that I was using.
So they were saying that we should be able to detect such things?
No, they're just simulating it. No.
Because if we live here and then there is some other people like doing crazy things there and like colliding black holes, they should affect our universe too.
No,
that would be like an indirect proof that
that there is another dimension. So this whole resulted in an album. So the title Micrometers Iris EFT 001. It was released on Touch Label. So Touch Label is a British-based label who also worked with Hildur Guðnadóttir. She won an Oscar for The Joker, and she did Chernobyl. So I was really happy to be able to release an experimental album on that label. And as also mentioned in the introduction, so we sent out a press release. So I had a press agency in Berlin working for the promotion of the album, and I had an assistant. And it was released in December, and we sent out the news in October. And 1 week later, it was, I think, I opened a website and I just opened DJ Mag, and all of a sudden, it was on the front cover next to the new album of Laurent Garnier and Billie Eilish. So we were like, okay, what is happening here? So it was really weird, a very interesting experience. So it was really hugely taken up by the EDM scene, electronic music scene. So from there, it spread out to Music Mag, Music Radar. So we were in the beginning in the US, then we were in Korea, in Japan, and then it started. So I think we traced it in 28 different countries.
Did you also go to the parallel universe?
No, that not. Yeah, that would have been nice.
You don't know.
You don't know.
Maybe.
You don't know. Might have.
What was interesting at that time, it was just before the Russian invasion, is that it also completely started going viral in Russia. And I didn't know because, of course, I don't speak Russian. I didn't expect it. And that was because people started contacting me via Instagram, that it was on Telegram there. And then I asked them to, okay, where did it appear? And then it was all Russian newspapers on the newspapers. So it was like, that was a parallel. Yes.
Can we listen to it?
Yes, of course. It's on Spotify. It's it's on all streaming platforms. If you check it, you will find it. So we had a lot of press coverage, not expected. And in 2022, as also mentioned, that was also very nice. It was picked up by Ars Electronica. So it's a festival in Austria. There's also a prize. There's several prizes. So you have the prize for more electronic art. And so the album got an honorary mention for the STARTS prize. So that's a prize that is being given to science, technology, and art projects. So that was also really nice to have it recognized because it was using sonification as a field also that also has an artistic validity. Of course, today I see a lot of people, also my students in the Netherlands, everyone is jumping on sonification. I think it's a new evolution. This is a trailer. This is a trailer of the album. So we also had a trailer. Here also there is I can show you there's some interesting geometries which are related to string theory. So in the process, I also work with a visual artist. So we also do audiovisual shows. His name is Jaromir Mulders, very talented visual artist. And he, so what we do is I give him models, sometimes 3D models, and he makes these beautiful imaginary new worlds with his own software, and then we combine it with the music. So there's some footage in it of a Calabi-Yau manifold. Maybe we can talk about it later. It comes from string theory, and it's related to more than the dimension that you are living in. No. Oh, and does it play? Yes. So that's a Calabi-Yau manifold. Yeah, and that trailer also appeared everywhere. So it was ripped very quickly, and then in Russia it was also on all those news they ripped they put their own logo onto it basically.
Yeah.
So,
But what's really interesting is in when we because I need to keep a bit an eye on time.
Yeah.
So if we look at well, sonification or visualization, you showed your book, and this is what I've been reading, and I find it stunning that they actually just use the same imagery in a way.
So it's same.
Black, blue,
it's
and white.
On the
So
cover.
on the cover, but on the cover. So this sort of cliche about what space is and how you depict it is I think very interesting, because you have a video of NASA. I don't know if that's a good moment to show it, but I mean, we've just heard your interpretation, which is completely different. And you have a video of NASA showing what it is to enter. And I would love it if you
indeed, this is work by Jaromir, so you see that it's a complete other language, because it's of course he's trained he works a lot with visual feedback. So if there are people in the arts,
but still there are relationships to the scientific world.
So
here like the probability of an electron.
Voila, yes, indeed. It's really nice. I like working with Jaromir so much because I tell him about the science. Of course, he's also very good in the coding and in conceptualizing the thing. And then he can make, so this he made using feedback, and I didn't give him a model, but he figured out he understands it so very well and he can add this aesthetic layer that's really fundamental to it.
There's a question.
Yes, I have a question. I'm fascinated by the dialogue between the two of you, and I'm also very puzzled by the gap between all the science and the visualization of science and publics, because you do performances.
Yes.
And in what way do you engage with publics in mediating all those scientific information and all this super thorough scientific practice that you have versus the visualization of it? Because I could be dancing on it at Tech or Electra, and it could be anything. So how do you bridge the gap?
No, that's good. Yeah, indeed. I mean, there's several dimensions to it. So the first dimension is, for us, it's important when you play an audiovisual show that we take people in another trip on a trip.
Mhm.
Without that they know about the science. It's also with the album. For me, it's important if you listen to the album that you're like completely immersed into it. But for the communication part, I also do lecture performances in which I talk about the science and give some more insight, tell stories, and also about the techniques that I'm using. And then I'm mostly, so I tell different stories, and then I play a part of a live track to disseminate it. So I also think it's very important, and I like to do it to make people see, because I've been working as a musician, I've been working as a mathematician, and for me it's the same. It's a very creative process doing science. But for people, it's still two separate worlds, and to show them.
But that is exactly what happens in art-science collaborations.
Yes.
That there's this understanding that scientists work very artistic and that artists can work scientific. I mean, that's the whole reason behind practical PhDs for artists.
Yeah.
So that these worlds are closer than you would think.
But in art science, sometimes I think it's still a lot the case that there's the artist and there's the scientist, and they're separated. And for me, sometimes it's very difficult as a scientist, because I have the luck that of course, I'm privileged that I had the luck to do PhD and blah, blah, blah. And to be in both worlds, you know.
It depends completely on the way how the scientist actually works. Because I made an exhibition in 2010 in Museum M on the collaboration between art and scientists, amongst others with psychologists. And they were very much, so the scientists there were very much, well, if the artists have a question, that they come to us. So that was really a one-way direction. So whereas with you two, the connection is much closer, especially in your case, Valery, because
it's in one person. But then the problem is, if you go to sometimes to the art science community, that they want to or put you in the artist category or the because it's very difficult for them to accept that you're maybe in both.
Quite
worlds.
often it's also the case that the artistic part is more or less an illustration of the science, and that's really
true.
dangerous.
That's true.
Well, I think what you mentioned, I think it's fascinating in the sense, but I think art science is polyvocal, and there's different models, and you can fall into the public education of science, but there's also the public experiment model that was brought up by, say, Born and Barry, or even the Ars Electronica published this super interesting paper about the emergence of a third space, and what are the methods that you can enable in advance to design that third space, and where the research object doesn't belong to art, doesn't belong to science, but it's kind of this external alien thing.
That's also what we're hoping to do with art science and the faculty in Den Haag, is to make a new field that's not art or science, but that's just a third, like a new kind of practice that encompasses the two. But it's very difficult to.
No, but what is interesting in this whole discussion is actually that it takes ages to get this done. Because I mean, if they're doing it now, and you talked about what they're developing at ULB in autumn, this is a discussion that goes on already. Well, from the end of the 60s, more or less, with organizations as Leonardo that organize these laser talks actually, and it's very interesting for me to see, because I was busy in the field, especially around 2007, 2010, and then got involved in laser talks. But very interesting to see that it's now being picked up again. So it comes in waves, really. So,
but what you say, it's interesting actually, because it's true that there is like two separate branches that try to join, which is you have arts inspired by sciences, and then like arts that thinks about black holes and like exoplanets and stuff. But then you also have sciences that uses the artistic channel to express.
I think we have to be very careful, because all this is pushed by neoliberal agendas. And I mean, I'm from Canada, Montreal, and like we speak about research creation, and we're privileged. We have like a lot of funding, we have tons of things, tons of programs that push those art science endeavors. But it's all about how can you create a research object that's high risk, high impact, high applicability, and all that. So it's very tricky. And this is where it's a slippery slope, where on one side, artists can be instrumentalized by science, on the other side, scientists can be also romanticized by artists. So it's a very fine balance where you, and I think that I'm sorry, I don't know your name.
Edith.
But it's you mentioned the question of time. It takes huge amount of time to implement those things.
And also awareness, because you need other kind of skill sets to teach other kind of skill sets to the I don't know how you would call them, art scientists, or you have to have a new name. But it's also looking what is the right skill set. And that's also, I think, in the Netherlands, what we're looking like, what would be, that is not completely artistic education, not completely scientific, it's a little bit in between.
I have a suggestion.
Yeah.
Try to be an architect.
Yes, no, but I think architects, I know a lot of architects are very good musicians and composers also. Xenakis, of course, he's the archetype, but there's a lot of...
Bob Wilson is an architect.
Okay, voila. No, but that's true, yeah.
Can we go to the video of the NASA?
Yes.
And then maybe we can slowly round it up as well.
Voila.
I also had a question for you actually, because you mentioned that thing about how this public is supposed to live the experience. And I was wondering if you know that the data you're dancing to, the music you're dancing to, comes from actual real data from black holes or from real pulsars that are just now beating. Does it change your experience?
I don't know. I mean, we've seen this aesthetics like again and again and again in electronic music festivals. I'm just wondering, like, okay, I will probably be absorbed by the aesthetic, the visuality, the embodiment, the sound system, and everything. But I think the concept of how did you call it? Concert performance?
Lecture performance.
But I don't know. I have no idea what it looks like, but it seems amazing.
That's something that is.
No,
but I think that the lecture performance is effectively one of the solutions to bring these worlds together.
But then it should also be, if you do a lecture performance, because then it's a little bit dated, it should also be a performance. You know, there's a performance.
There's a balance between practice and
because then you have to be you have to you should entertain all, and that maybe it's not a dirty word meant, but just to take. I always believe telling stories and taking people on a sort of trip.
Yeah, but if it's instrumentalized, as you say, for another good, then you have to be very careful.
Then it's dangerous. Yeah, that's true.
You can trick people into getting interesting to sciences. I don't have a problem with that. It's okay.
Like
so you're gonna see something, and then I'm gonna tell you what you saw, or I'm gonna tell you beforehand that it's gonna be fun, and I'm bringing you to an evening, and you believe you will have fun, but it will start with a sort of fun 15-minute lecture about
MDMA.
You told it.
Another observation that science is moving into a realm that things are not provable anymore. Now a lot of theories are based on speculation.
Yeah, maybe.
There is the Large Hadron Collider, and you can prove a few things, but like string theory, you cannot prove it anymore.
No.
You can hypothetically think about it, and you have different models to think about, and it's a clash, but the thing is, art is also there, I think there is now a big openness for artists interpreting the world and also scientists, but you used to have proof in the background to say, this is true because it works.
So when
but that is for me the link between art and theoretical physics is imagination. That's because if you go farther and farther away, it's about speculation, interpretation, and very interesting, all your personal history, your culture also starts to play a role, also scientifically. Your belief systems. And
in that sense, it's also, I think, very important in the political times we're going through. There's a lot of attention.
It takes away the objectiveness of science.
But then I don't think I would agree with that, actually. So when I said we don't prove physical laws, that doesn't mean that we don't have to agree on physical results, or to agree that we proceed along with the scientific method, for example. When I say we don't prove Newton's laws, no reasonable physicists in the world won't agree on it. So we all agree on it because we repeat an experiment a lot of times.
That's not true for
so it is not true for string theory, but if I tell you, if I ask you do an experiment proving Fermat's theorem, for example, That's just
Fermat's
Fermat's
Yeah,
Fermat's
yeah.
last theorem, or whatever.
Yeah.
Okay.
It's a philosophical discussion because even in mathematics, if you go into the foundations, there's a whole study of foundations of mathematics.
Mhm.
One very fascinating question I also teach on mathematics and art and in my students is like, what on earth is a triangle?
Yeah.
How can you? We only think
It's a
of
convention.
representations.
It's a
It's a representation. It's like the cave of Plato. You can only think in mathematics of representations of concepts in a sort of a hypothetical mental construction. Because a triangle can be, for me, it can be 3 dots that I voila, or it can be also, you can represent a triangle as 1, 2, 3, and you connect, you can do it algebraically. So these are all different kind of representations of the idea of a triangle.
Well, then there is a guy who like proved that 1 + 1 is 2 in 400 pages.
Yeah.
So that,
Yeah.
I mean, so that's another thing. So, but to come back at string theory, I don't want to. But string theory, it's true that you don't have an experiment that currently can confirm or infirm it, but it's more a mathematical construction that is extremely solid.
But that
So
can change as well. I mean, the
So,
fact that we can't,
well,
we can't prove it today doesn't mean we can't
of
prove
course,
it in 20
of
years.
course,
Maybe,
and
maybe.
I think
Yeah,
people
maybe.
believe there will be a day,
Way.
a way,
Yeah,
one
yeah.
day to prove it. But what I say, it's solid. It's mathematically solid. It's not that I can come up with like some crazy things and say, oh, those little strings. It's not that people came up with little strings because it was cool.
But it is like Higgs
Huge
boson
little
was predicted
strings,
like
yeah.
20 years ago, and finally they could prove it in the last
Sorry, but
Higgs boson.
The Higgs, yeah,
That was-
but there
Oh,
are,
that was in the
Long way
50s, and they observed in 2013. So I think, no, sorry, it was in the
That
60s.
distance is always getting bigger, you know. Like,
yeah,
I'm
but
sort of
in
afraid that
in string theory, one of the questions is, for example, in brain cosmology, do we live in a 4-dimensional space-time? Maybe we live in a 10. No, we can live in a 10-dimensional one or a 5. And there are being experiments done using data coming from space to check if there is more than 4 dimensions. And I really hope, I think in a couple 20, 30 years, we will have the answer.
Yeah.
And maybe we will see we
And
live
it
in a
might
10-dimensional
have
world.
been that the experiments at CERN could have discovered an extra dimension because energy
yeah.
was lost somewhere, and if energy is
Yeah.
conserved in 4 dimensions, but if it's lost
Yeah.
somewhere, that
Yeah.
doesn't indicate.
I was just stressing the fact that science becomes a bit hypothetical and art is something that's purely hypothetical from the imagination, that there's a nice.
No, it's the same with evolution.
But I think science is really held to really strict standards.
That's why my
I think you
phone
don't
works.
really joke with the concept of hypothesis,
Yeah.
the regimes of validity of the theories that you work,
But
mathematical consistency. I think that's it sounds less fun. I agree that just like letting your imagination run. But it is true that.
No, but if you're thinking about the hypothesis and the whole, but this also can change very quickly, of course, with the rise of AI, the search for AGI. If we will have, they estimate that by 2030 we might be having AGI, artificial general intelligence. I don't believe but we will have systems, and that will not be so far away, that the AIs reconstruct themselves and improve themselves and start creating theories. And then we will be in a situation where we'll.
I think they have tried this. Yeah, you feed an AI with data. Can you find? Okay, you feed the data of all the planets and the star moving in the universe for the last 100 years.
Yeah.
And can you find Newton's laws?
Yeah. And
will it find? It doesn't find.
No.
No.
No,
Doesn't find so far, as far as I know.
That's very simple because artificial intelligence doesn't have senses. It cannot hear, it cannot smell, it cannot feel. It can only use language-based systems.
But then eventually,
it's multimodal now. It can use video. It can annotate pictures. You have large language models, so it can reason. But it's growing and growing, and it's going at an exponential rate.
So
every 10 months,
so the scientists of the future are going to be AI. Then.
Yeah, I think it's going to be partly AI generated. I think so. And then the problem will be you will have a theory, but how does it work? I mean, that's going to be
Yeah, the problem with the black box is that we don't know how it. So I know that it solves some problems. For example, can you? There was this thing about it's not true. So feed the AI with motion of planets and find laws.
Yeah.
And it found laws, and it found that these laws are valid in 4.3 dimensions. So it had the conclusion of the AI was that our universe had 4.3 dimensions.
Okay.
But of course, we have no clue. I think that information is close to useless, actually, because we are not so interested into the final answer. We are interested to understand how that answer came about. That's
At the
interesting
same time,
to
you don't
us.
know where it leads us to.
Otherwise, it's just like, okay, well, it's 4.3 and that's it. It's
Yeah.
like the answer is
Yeah.
42, and then we have no clue what it means. But
Yeah, question?
Sorry, I was wondering, because we're mentioning AI, has it already influence in your practice, in your work? Have you started to use it, or you think it can be interesting sonification?
my students did. My students are using it.
Yeah.
I'd have to check that
But
there.
also in your practice, because you're talking about the AI scientist.
I switched from data science. I'm now working as an AI engineer, partly. Yeah. So and also artistically, I'm looking into the possibilities for sonification and to go beyond sonification. So of course, yes, there's a lot of possibilities. But as you say, the only problem is the whole black box methodology. That's a little bit a shame. There is being theory developed in AI of trying to come up with other AIs that try to explain how another AI works. It's a whole new field. Yeah, there's a lot of new fields coming on. Another field is, of course, the ethics of AI is also a huge field. Also the security, because it will have a lot of security issues. But the explainability is also another field. Yeah, because if you're using a large language model, you feed it with, it's just GPT-3 has 175 billion parameters, knobs that you tune. That's 3.5, and now we have GPT-4. They don't want to expose anymore how many parameters they have, so everything is closing down from OpenAI because of the competition.
Closed AI now.
Yes, yeah. And every 6 months they go with a factor times 10. So
Yeah, I think, and I think in physics, I have to admit that AI are really good at certain like semi-mechanical things. So coding, translating a code in from one language to another, it's pretty good at doing this.
Yeah.
So there are certain things. Of course, there's a usual you write some introduction for some paper, and you want a spell check or grammar check that has always been in the cards that had to work. So that's pretty good. But I tried something for fun. So this year I had master students doing their master thesis with me, and I asked, so write a master thesis for the physics department at ULB, 50 pages that would like make a 17 out of 20 grade, and the theme would be asymptotic symmetries of plane waves. So it wrote something, and I was surprised actually that the table of contents was not that bad. It was sort of the logic behind the structure of the argumentation was correct. At the table of contents, I could have been tricked. But then when you check what's written, what's written is completely wrong or complete nonsense or whatever. But still, I think it's getting better. So I don't know. It's a matter of time before.
Yeah.
But it's not necessarily bad. I mean, 200 years ago, people didn't have calculators, and people knew how to compute much better than we did.
But the only thing that it is it's very invasive for climate change. The energy consumption. That's also, there's a paper by a young AI guy.
I've read about it.
Yeah. So he explains by 2030, 1/5 of the energy consumption production in the US alone will go to the AI systems in the US. So it's
If they don't solve that problem,
it's gonna be it's a huge problem.
Exactly.
Yes.
So I try again. Can you?
I can show you the NASA video.
The NASA video.
Let me first tell you something about Interstellar, because I don't know if I told you that I like Interstellar.
Not like half an hour.
No, just what time is it? Oh, it's already done.
Yeah.
Okay. But just to make some advertisement for Interstellar, I think it's really
Do you have bones in them?
It doesn't
Shares.
But it's one way actually to. So we discussed about the fact that sometimes arts use sciences in in a free way, And I think that movie falls more into the category that it's more like a scientific movie that uses the artistic channel to express some ideas. So it was really staging a lot of real things in general relativity, in maybe even in string theory a little bit, and it was making a whole story around it just to illustrate these things. And I think a lot of things are extremely precise in that movie. There were like lots of layers of reading to that movie.
Yeah.
You can see
But Kip Thorne was involved. So
Kip Thorne was involved, and he's a
Yeah.
Nobel Prize in physics. And so what's interesting about this thing, for example, this picture that you see in Interstellar. So, I was trying to say, well, is this a real thing? And then, of course, why do you have this picture? That's a crazy picture. But actually, what you see is that this is a black hole, and you have an accretion disk around. So an accretion disk is just you have a black hole and matter going around the black hole. And so that matter emits light. So why is it so? This accretion disk goes like this, just around. So isn't it in this plane? So why is it that you're seeing this crazy thing here? Well, the reason why you see this crazy thing here is that the light of the disk behind the black hole, if space-time was flat, it would just like go a straight line, so you wouldn't see anything. But actually, because black holes curve space-time very much, light from behind actually are bent and arrive to your eye. And this is why here you see something. There's nothing here, actually. But this is the matter, the light behind the black hole that has been bent. It's just for fun. I just like, we just did this with one of my students. We just wanted to compute these things. So, okay, of course, it's not as nice as that thing. It's something that you did with a laptop in 5 minutes if you want, but not in 5 minutes, but computing the thing. So this is just computing the trajectories of light rays in the geometry of a black hole, and you see it's exactly the same thing that they found in there. Of course, they had supercomputer and stuff. That's Hollywood, but we are ULB, so it's not the same thing. And so I had a student doing this computation. You can also see it change the angle of vision and stuff. Well, it's a bit slow, but okay. No, what is the connection? So remember this picture I showed you, this little orange blob. So actually, if you take the picture in Interstellar and you change the angle of view, so now instead of looking in the plane, you start going around the black hole and viewing it from the top. Then when you do this, this is the sort of thing that happens. And then the picture that you get, okay, that's the picture that you get, and then you start blurring it because the telescopes are not like optimal and stuff. This is what you get, and you get exactly the picture that they observed. So that's one connection. Actually, the picture, the thing that we were getting in Interstellar, where actually real computations, they even made scientific papers out of the codes and the thing they designed in the movie. So now, okay, here we come to the NASA video. So the thing is that what's really interesting about black holes is that a lot of really weird things happen in their presence. So if you just throw a camera inside a black hole, you will see some things that are really crazy because of the same reason that so we have something that is called gravitational lensing. Because space-time is curved, light will not go in a straight line. So you will see light coming from all different directions that will completely blur your senses. So that's a video that they made at NASA. And one thing is that if you are thrown into a black hole and you see what's happening, light gets distorted. And this is the thing that you would see. So here,
it's
essentially,
not only the visuals, but it's also the sound.
Yeah. We have to discuss. So let's see if the sound works. So that's the guy who recognized the thing. Now we know the picture, and now the camera is just flying into the black hole. So that's called the photon ring here. The horizon is inside. There you cross the photon ring, which is some light ring around the black hole. And now you cross the horizon. So now you can still get light, but you cannot escape. You're just getting light from the outside now. And now you reach the center of the black hole. And then you don't see anything anymore. Less and less. And then you are crushed. So that's...
But the soundtrack is just so... It's if we compare it with what Valery does, it's something like, because that is also the problem. We discussed it briefly before we started. But if you look at any kind of film on nature, they put this kind of music soundtrack as well in the back. Like you can't see a fish swimming without a soundtrack where he's sort of doing I don't know what. Or giraffes in a plane is also one of the favorites, I think.
I don't know. I think it works.
Yeah.
I liked it. I liked it.
But you have another little one.
Oh,
do you have that
no.
Dropbox one? And then we finish.
Then I have the other one.
because,
So that's the thing that NASA did, and then there is the thing that we did.
with the violin.
The thing we did is a different thing.
No, but really.
It's with the violin. So what we did is imagining that we are drawing. There is a show that we prepared with Benjamin Glorieux, Claes Verpoes, and Vincent Kars. The idea is we have a cellist playing, and the guy plays, and we throw into a black hole. What would we hear? Okay, and so we have this like huge installation with like visuals, a sound engineer mixing the sound to represent how the sound is mixing, and then we have the cellist playing Bach Partita, for example, and then see what it sounds like. So that's the simulation that I did with collaborators. So that's another thing. So here, what we are seeing. So okay, here we have a cellist. Actually, no, that's not the cellist. That's going to be a full orchestra playing the Interstellar theme, because I don't know if I told you that I like Interstellar. And then what we computed was how the sound would get distorted. So we are outside of the black hole, far away. We have the orchestra playing, and then we throw it, and the orchestra starts whirling around the black hole. How would it sound like? And so we discussed the fact that time flows in a different way, so you would hear things differently. And so this is a simulation that we did. So the blue dot, that's us, and then there's that's the black hole. We are viewing the thing from here. So when the thing starts going around. So forget about the second one, just focus on the white one. We see the time, we can hear that the sound is distorted. And something funny will happen when he will pass behind the black hole. In principle, we wouldn't hear it anymore because it's behind the black hole. It would crash the sound waves, the light waves signal would crash into the black hole. But because of what I told you, we will still hear it. When it goes behind, we'll do something like this. And just like this. So there it was behind the black hole, but still we could hear it, because the light signals were flowing over the black hole and still reaching us. So this is the trajectory, and this is us. So it's a bit.
But have you ever thought about like experimenting with VR sound and VR experiments and immersive media?
Actually, so the performance we do, the sound engineer, he likes to use all the speakers that are at different like levels and different layers, and he projects the sound that is supposed to represent where the cellist is. So, but I personally don't know anything about it, but I know this is something that he pays attention to.
So there are parallel.
So that's the sort of thing.
Black holes, worlds of black holes with different sounds. Are you currently developing other work?
Sorry. Yeah,
Valery?
okay, you meant to.
Oh, sorry.
Sorry. And that's the exhibition that actually uses this computation that we did, where we have the cellist getting closer and closer and closer to the black hole. At some point, he enters the black hole, so we don't hear anything anymore. Mm-hmm. But then enters the second part of the show where information was destroyed. The cellist is thrown into the black hole and he's crushed. But actually, as I told you earlier, black information is not really destroyed. It's recovered in a really scrambled way. And you have to wait long enough to be able to reconstruct the information. And so the second part of the show is when the information gets back, and we start reforming the Bach partita that he was playing through Hawking radiation. So that's something we try to.
Okay, Valery, what are you developing currently?
Now looking for a new Micromeras series, but the idea is to go more into the mathematics.
Okay.
Of maybe string theory and even go more theoretical. So I'm working with a professor of the University of Antwerp who specialized into some. These are mathematical structures that I also studied in my PhD.
Mm-hmm.
What's his name?
David Eelboeren. He's also writing books on mathematics, little books. And the idea is also because in my PhD I was studying mathematical structures related to superstring theory, But the cool thing is, well, it's a little bit, they're very beautiful, but of course it's very difficult to, again, explain and show it to other people. And the geometries that I was studying can have many dimensions, which was really cool, because in my PhD I had to make them 3-dimensional intersections, but it would be really nice to find ways to visualize them, and also sonify, and to use maybe VR, that you could really.
Okay.
So it's going to be even more into the theory. Yeah.
Okay.
What structures were you studying?
Those are the structures that I was studying are called buildings. So these are generalizations of generalizations. There is sort of generalizations of the idea of the Greek that the Greek had. So probably the Greek scientists, they didn't know about the number pi. They only knew it that if you have a circle, and it's just a connection between algebra and geometry. Yeah, that's a little bit. That's at the heart of those two. Yeah.
Okay, thank you. Are there questions, or are you completely flabbergasted and in need of a drink?
I have one question for the scientist.
Well, he's.
But you mentioned really in the beginning, you said that gravity instantaneously stops when the source disappears. But is that like sort of same? According to
Newton, it's not true, eh?
This is no. This is.
I saw a similarity between like the what's it called? When two things are
Entanglement.
Entanglement.
That's something different. Yeah. No.
But there is but it's not true. So
No.
No,
gravity travels at the speed of light.
It's not the same. Yeah, it's not the same thing. Here, it's just the observation that the formula tells you that the force is proportional to mass 1 times mass 2 divided by the square of the distance. So if mass 1 disappears, well, there's no way to tell you how gravity propagates in Newton's theory, because if m1 becomes 0, well, F instantaneously becomes 0 as soon as you have put m to 0. But you have the same problem actually in electrostatics. If you look at Coulomb's law, Coulomb law, it looks a little bit the same. You have two charges, Q1 and Q2. Well, the force between the two is Q1, Q2 divided by the square of the distance. But then the Coulomb in electrostatics, you know that's not the whole story. You know that the whole story comes with Maxwell's equation and then quantum electrodynamics and these things. So essentially, what Einstein was trying to find was to find to Newton's law what Maxwell's equations were to Coulomb's law in a way.
But the big problem in quantum gravity, it's like if you have a theater. If you look from Newton or quantum physics, you have the theater that's our reality, 3-dimensional reality, and then you have time that's separated. But what Einstein did was said, no, time is going to be in the theater. It's going to be part of the theater. And that's the big difference. And that's also the problem in quantum gravity. I think one of the main questions, as I see it, is that as physicists, we don't understand time. I mean, what's the difference between the time dimension and the spatial dimension? Why is it so different? Well,
you said we don't know why there are 4 dimensions, 4 space-time dimensions. Why is it that there is only one time dimension?
Yes, because you can also have, and it's one time. Why is it not 2 times or 3 times?
But it's also very subjective time.
And it's subjective. Is it an anthropocentric thing, time, or
well, I would say that time is relative, but is objective. I think that duration is subjective.
Yeah.
I would say.
What?
I don't know. I would say that time is objective, but is relative. But that duration is subjective. The duration, the perception of time is subjective, but.
What is again the end of Interstellar? I don't remember the end of
well, he come back. So no, it ends well because he sees Murph again.
No, but some people
sees Murph again.
Yeah, exactly. I don't see it.
No, they die. They all die.
Yeah. So.
No, but it's Hollywood. They save the world.
Thank you very much, Stephane. Thank you very much, Valery. Thank you very much for you all being here. And so we're preparing, Alexandra is already preparing another laser talk in a couple of
Yes,
can
it
maybe
will be
announce
on next laser talk will be on the 2nd of July, and it will be about environmental justice, and it will be in June.
Yeah.
Ah, yeah.
Yes.
Yeah. And then we're preparing laser talks for autumn again. So
Yeah.
thank you.
Thank you.